KFC's chicken starts in giant seasoning drums, where secret spice blends coat every piece to perfection. McDonald's burgers move through sizzling conveyor grills as Subway's fresh loaves rise and bake by the thousands each hour. Today, we step inside the kitchens and factories that power the world's biggest fast food empires to see how consistency, speed, and flavor come together on a global scale. KFC's fried chicken may be iconic for its secret blend of 11 herbs and spices, but the factory process behind every crispy, golden piece is built on something far less mysterious: precise engineering, timed workflow, and ruthless consistency. Behind every bucket of original recipe is a production line designed to turn raw chicken into seasoned, breaded, and pressure-fried perfection on a massive global scale. Millions of pieces per day across thousands of locations, all starting in high-throughput poultry processing facilities. The process begins at the poultry plant, long before any chicken sees a fryer. KFC doesn't raise its own chickens. Instead, it partners with large-scale poultry suppliers who specialize in high-efficiency, vertically integrated operations. These facilities process thousands of birds per hour using lines that are fully automated and regulated to deliver uniform size, weight, and quality. Once chickens arrive at the facility, they're stunned and humanely slaughtered, then passed through defeathering machines. The birds are washed, eviscerated, and chilled in cold water or air-chilling tunnels, depending on the region and regulatory requirements. From here, they move to automated cutting lines, where high-speed blades segment each bird into standardized cuts: drumsticks, thighs, wings, and breasts, with specific sizing tolerances so each piece will cook evenly during pressure frying. Every piece is trimmed and inspected, then sent through water jet portioning systems, lasers, and nozzles that precisely cut meat based on optical sizing. Pieces are sorted by weight to ensure uniform cook times, then chilled to below 40 degrees Fahrenheit and packed in vacuum-sealed bags. These raw chicken portions are shipped to regional KFC prep centers or directly to KFC kitchens, depending on location. At centralized KFC prep facilities, often located near urban hubs or distribution centers, the real transformation begins. Here, each piece of raw chicken is thawed, if frozen, washed, and carefully inspected again. Workers wear full food-safe suits, gloves, and hairnets, operating under strict HACCP protocols to avoid cross-contamination. Every batch is handled in cold prep rooms, where the air is chilled and filtered to keep bacterial growth to a minimum. Then comes the marination phase, a foundational step in the flavor and texture of KFC's chicken. Each piece is soaked in a liquid brine, typically a mix of water, salt, phosphate, and other flavor-carrying compounds. The phosphate acts as a moisture-retaining agent, helping the chicken stay juicy through frying. This brine is vacuum tumbled into the meat using large rotating drums, which massage the liquid deep into the muscle fibers over the course of 30 to 60 minutes. Every load is weighed before and after to ensure absorption is within spec. Next comes seasoning. Contrary to myth, the famous 11 herbs and spices are not mixed at every location. Instead, the spice blend is produced at a secure, centralized facility, where the exact combination is pre-measured and packed into coated, tamper-proof bags. These bags are shipped to prep centers or stores, where they're added directly to flour for the breading process. Only a few people in the company know the full recipe, and the factory itself is designed to prevent accidental or deliberate disclosure. Even the workers handling the blend often don't know what's in it. In the prep facility, seasoned breading stations are set up in long rows, where chicken moves through the legendary hand breading process. Each piece is dredged in seasoned flour, then placed in a shallow basket, where it's pressed into the flour with a very specific folding and compression motion. This step, called the 7-10-7 method, is taught to every KFC cook and replicated in prep facilities worldwide. It's part of what gives KFC chicken its craggy, crunchy, uneven texture. The breaded pieces are then loaded onto trays and either flash chilled for shipment or sent directly to in-house kitchens for frying. In some markets, partially cooked chicken is sent to stores to shorten fry times during service rushes. But in most regions, frying is done fresh in-store, using the same tightly controlled procedure. In KFC restaurants, pressure fryers are the beating heart of the operation. These aren't just deep fryers, they're sealed, industrial pressure cookers that fry chicken under high pressure and temperature. The typical fryer operates at around 350 degrees Fahrenheit under 12 psi, allowing the chicken to cook faster and retain more moisture than open frying. The result? A crisp exterior with a tender, juicy interior, cooked in about 10 minutes per batch. Each piece is loaded into a wire basket or chicken clamshell, arranged in a way that ensures even oil flow. The basket is locked into the fryer, the lid is sealed, and the cook cycle begins. Once complete, the fryer releases pressure and the basket is lifted. Every batch is placed on a draining rack, where oil drips off and the crust sets. From there, chicken is either held in warming cabinets kept at a specific humidity and temperature, or served immediately, depending on demand. Quality checks are frequent. Staff use thermometers to confirm internal temperatures, visual checks to verify color and breading coverage, and taste tests to ensure consistency. Any batch that sits too long is discarded to maintain quality standards. Back in the prep centers, not all chicken ends up as original recipe. KFC also produces extra crispy, spicy, and grilled varieties, each requiring slightly different breading and cooking profiles. Extra crispy chicken, for instance, goes through a double breading process with a coarser flour blend and is fried in open fryers, not pressure ones. The breading station must be cleaned and reset between batches to avoid cross-contamination between flavors. Meanwhile, grilled chicken is seasoned differently, rubbed with a dry spice mix and roasted in combi ovens, not fried at all. These ovens use steam and convection to cook the meat evenly while keeping it juicy. The flavor is more subdued, but the factory process behind it is just as strict, with marination and seasoning steps done under cold room conditions before transport. Throughout the entire system, data is king. Every batch of chicken, from farm to fryer, is logged with timestamps, location codes, and supplier data. Digital systems track everything from fryer oil turnover rates to breading mix usage, ensuring that no store deviates from standard operating procedures. Even the oil itself is filtered between batches and replaced on a tightly controlled schedule. Sensors monitor fryers for temperature drift and alert staff if anything strays outside of spec. Sanitation is constant. Between batches, breading stations are cleaned, gloves are changed, and utensils are sanitized. The entire prep room in a factory is stripped down at the end of each shift and pressure washed with food-grade disinfectants. Air in the facility is filtered and recirculated to control temperature and humidity. Workers follow strict entry protocols, passing through air curtains and sanitizing stations before handling any food. And while the public rarely sees it, KFC's factory network is global but highly localized. Facilities are located close to supply chains and restaurants, so that chicken can go from bird to bucket in as little as 48 hours. Some regions operate their own prep hubs, while others rely entirely on in-store breading. Regardless of setup, the steps, the cuts, the brining, the seasoning, the breading method, the pressure fry cycle are replicated with uncanny consistency, batch after batch, store after store. So even though the end product might look simple, a crispy thigh, a golden drumstick, a perfectly breaded breast, it's the result of a highly engineered process that controls every variable, from feedlot to fryer. Every bite of KFC chicken is a small miracle of industrial food science wrapped in proprietary seasoning. and delivered at a speed that only automation, logistics, and relentless procedural training can provide. McDonald's burgers may feel like fast food, but behind each patty is a global factory system built for scale, safety, and precision engineering. Millions of burgers are served every single day, and nearly all of them can be traced back to a production process that transforms whole sides of beef into standardized, flash-frozen patties in minutes. At the factory level, making a McDonald's burger isn't about cooking. It's about control of sourcing, fat content, texture, shape, temperature, and microbiological safety. It's meat processing at the scale of aerospace manufacturing. It all starts with the raw material, beef trimmings. McDonald's doesn't use mysterious filler meat or pink slime in its regular burgers. It uses 100% beef, mostly lean trimmings left over after the most valuable cuts, like steaks and roasts, are removed from the carcass. These trimmings arrive at the processing facility in large vacuum-sealed containers, chilled and tracked by batch number and origin. Every shipment is tested before it's even unloaded, scanned for temperature consistency and contamination. Inside the facility, which is refrigerated from wall to wall, the beef moves quickly from receiving to grinding, but not before it's blended. Each patty, whether for a Big Mac, a quarter pounder, or a basic hamburger, has a target fat ratio, typically around 20% fat to 80% lean. Because beef trimmings vary in fat content depending on where they come from on the cow, the factory uses a fat analysis system to create the perfect blend. Optical scanners and near-infrared sensors analyze the fat levels of incoming meat in real time. The system then pulls from different bins of lean and fatty meat and blends them together, like dialing in a recipe by percentage. This blended beef goes into massive grinders, long stainless steel augers that push the meat through ultra-sharp blades, creating a uniform texture. The meat is not overly ground. The goal is to keep the bite structure intact so the patty doesn't become mushy. From here, the ground beef flows into a forming machine, a high-pressure system that presses it into exact size patties using precision molds. Each mold is designed to create uniform diameter, thickness, and weight. For example, a quarter pounder patty is exactly 4 ounces before cooking, while a standard hamburger patty is closer to 1.6 ounces. The forming system presses the meat into a specific density to account for shrinkage on the grill, ensuring that even after cooking, it fits the bun perfectly. But here's where the engineering gets fascinating. McDonald's patties are never seasoned, never pre-cooked, and never touched by human hands once they enter the forming line. The formed patties drop directly onto a freezing conveyor belt, where they're flash frozen at 40 degrees Fahrenheit within minutes. This rapid freezing is crucial. It locks in moisture, halts microbial activity, and stabilizes the patty's shape. The faster the freeze, the smaller the ice crystals, which means better texture when cooked later. As patties move through the spiral freezer, they are spaced evenly and continuously monitored by infrared temperature sensors and metal detectors. Any patty that's not perfectly shaped, underweight, or too warm is rejected automatically and diverted for reprocessing. Frozen patties are then stacked into rows by robotic arms and inserted into cartons. These boxes are barcoded, batch-coded, and sealed, then loaded onto pallets for deep frozen storage at 20 degrees Fahrenheit, ready to be shipped to McDonald's distribution centers. Throughout this process, every movement is tracked. Each patty has a data trail that includes time of production, meat origin, grinder settings, fat ratio, freezing time, and packaging line number. Back at the restaurant level, things are equally standardized. Frozen patties arrive in boxes labeled by product type: hamburger, quarter pounder, Big Mac, and are stored in walk-in freezers. When it's time to cook, grill operators pull the exact number of frozen patties needed and place them directly onto clamshell grills. No thawing required. These grills, automated and heated on both the top and bottom, close over the patties and apply uniform pressure and heat. A standard hamburger patty cooks in about 42 seconds. A quarter pounder, which is made from fresh, never frozen beef in some markets like the US, takes slightly longer and is grilled manually in order to preserve texture. The grills are calibrated down to the degree and the cooking time is preset. There's no guesswork, only automation. As the burgers cook, excess fat and moisture drain away through grooves in the grill, while sensors monitor temperature to ensure food safety. Once finished, patties are lifted by the operator and placed into holding trays, where they're kept warm for a maximum of 10 to 15 minutes before being discarded if not served. Another strict quality control rule. No seasoning is added during production. Only salt and pepper are applied after grilling, just before the burger is assembled. This ensures the seasoning is fresh and that the meat surface stays dry enough to achieve the Maillard reaction, giving the patty a browned, flavorful crust. While the patty is the star, the buns are also factory made for exact compatibility. Hamburger buns are baked off-site in high-speed bakeries, cooled, sliced, and flash frozen to lock in moisture. They're toasted at the restaurant on dual contact toasters that heat them to 500 degrees Fahrenheit for just a few seconds, creating a warm surface that resists sogginess and clings to condiments. Each component, from the beef to the bun, is timed, measured, and assembled within seconds at the line. An average McDonald's kitchen can assemble hundreds of burgers per hour, all with patties that are nearly indistinguishable in shape, taste, and texture, because the factories that produce them are engineered to eliminate variation. Sanitation in the patty factory is non-stop. Every surface is stainless steel. Workers wear full-body protective gear, pass through air showers, and sanitize hands and boots before entering food zones. All grinders, forming machines, belts, and hoppers are cleaned in place using high-pressure foam and steam sanitation systems. Air is HEPA filtered to prevent microbial spread, and environmental swabs are taken daily for bacterial testing. No part of the system operates without data. Every piece of equipment, from the meat blenders to the freezers, feeds information into a central dashboard monitored by food engineers and safety personnel. If temperatures shift, blade pressure fluctuates, or a batch goes even slightly out of spec, alerts are sent immediately, and the line can be stopped in seconds. Even the sustainability goals are tracked here. Many factories have adopted water recycling, energy-efficient freezers, and methane recovery from meat waste. Trimmings and rejected patties are rendered and repurposed, not wasted. At full capacity, a McDonald's beef patty plant can produce over 2 million patties per day. And despite that staggering number, the quality targets are tighter than many artisanal kitchens. Each burger you unwrap may feel mass-produced, and it is, but it's made in a system where every variable is measured, every motion is repeatable, and the only acceptable outcome is a patty that cooks the same way, looks the same way, and tastes the same way, anywhere in the world. So while the end product may feel fast and disposable, the factory behind every McDonald's burger is anything but. It's a cold, stainless steel symphony of grinding, forming, freezing, and packaging. A controlled ecosystem designed to deliver something incredibly consistent at a scale few other food systems can match. Subway may be known for its made-to-order sandwiches, but the illusion of freshness at the counter is only possible because of a vast, behind-the-scenes production system. One that begins in massive factories designed to produce pre-portioned, pre-baked, and ready-to-build components for every sandwich on the menu. From the foot-long bread to the uniform stacks of meats and sliced vegetables, nearly everything is prepped in specialized food manufacturing facilities that run 24/7 to keep up with the chain's global demand. It all starts with bread, the literal backbone of every Subway sandwich. Despite being baked in-store daily, Subway's bread dough is actually produced in massive bakery plants before ever reaching a restaurant. The factories, often contracted to industrial bakers specializing in frozen dough, mix thousands of pounds of dough at a time using high-speed spiral mixers and automated ingredient feeders that weigh flour, water, sugar, yeast, and conditioners to tight tolerances. Each type of bread, Italian, 9-grain wheat, honey oat, Parmesan oregano, hearty Italian, and more, has its own dough formula. Once mixed, the dough is divided into loaves using volumetric dough dividers that cut by weight, not by length, to ensure uniform baking later. The portions are gently rolled and shaped into long, narrow sticks on molder conveyors, then deposited onto baking trays. These trays pass through a proofing tunnel, a warm, humid chamber where yeast activates and the dough rises to its final size. But they're not baked yet. Instead, the risen loaves are par-baked, partially cooked just enough to set their structure and kill the yeast. This is done in high-capacity convection ovens running at over 400 degrees Fahrenheit. The loaves spend just a few minutes inside before being cooled with filtered air, then flash frozen on a spiral conveyor. The rapid freeze locks in moisture, preserves yeast flavor, and prevents the crust from hardening. These frozen, par-baked loaves are packed into boxes and shipped in temperature-controlled trucks to Subway locations around the world. At the store level, employees complete the baking in small convection ovens, giving the bread its warm, crusty exterior and that signature fresh-baked smell. But the structure, size, and flavor were all engineered weeks earlier in factories running like clockwork. Next up, meats and proteins. Subway's proteins are not sliced fresh in store. Instead, they're manufactured in large-scale food processing plants where uniformity is paramount. Turkey, ham, and roast beef begin as whole muscle cuts, often sourced from partner suppliers, and flash frozen upon arrival. These cuts are trimmed, brined, and then steam cooked or roasted in industrial ovens that hold hundreds of pounds of meat per batch. Brining is done under vacuum pressure to ensure full absorption of salt and flavor throughout the muscle. After cooking, the meats are chilled rapidly in glycol-cooled tunnels and sent through high-speed slicers, which slice each piece to exact thickness tolerances, usually just under 2 mm. The slices are then stacked and portioned mechanically. For instance, every serving of Black Forest ham is 4 slices, and every turkey portion is 6 slices. These are weighed automatically, with robotic hands inserting them into vacuum-sealed pouches. Each pouch contains a precise, ready-to-use portion, reducing prep time in stores and eliminating the chance of over-portioning. Subway's more processed meats, like cold cuts, salami, pepperoni, and bologna, are made through emulsification and casing processes. Raw meats are ground and mixed with spices and curing agents in vacuum blenders, then extruded into sausage casings or molded into loaves. These are cooked, chilled, and sliced with ultra-thin circular blades, moving at high speed before being packaged in airtight stacks. Then there's chicken, which comes in several forms: oven-roasted breast, grilled strips, breaded patties, and shreds for items like the rotisserie-style sandwich. Chicken breasts are tumble marinated in massive drums, where flavor and moisture are distributed through mechanical agitation. Grilled strips are cooked on conveyor belt broilers, where radiant heat and searing rollers cook both sides simultaneously before cutting into uniform strips. The cooked chicken is then chilled and packed into food service bags with oxygen absorbers to extend shelf life. Protein items, like meatballs and steak, are also made off-site. Meatballs are machine-formed, cooked in steam ovens, and flash frozen in their marinara sauce. Steak is pre-cooked, sliced, and frozen in bulk bags, often with added broth or seasoning to enhance juiciness once reheated. Nearly all of these proteins are delivered frozen or refrigerated, depending on local food safety laws and distribution times. Subway stores store them in walk-ins or lowboys, where they're portioned and prepared according to daily demand forecasts. What about vegetables? Most are pre-sliced, bagged, and shipped in cold chains from regional produce hubs. Lettuce arrives shredded. Tomatoes, cucumbers, green peppers, and onions are sliced in high-volume produce facilities using industrial slicers that sort by size, color, and ripeness. Carrots are often pre-julienned. Olives are pitted and sliced by weight, and pickles come brined and pre-cut. These produce plants clean, sanitize, and process vegetables in washed zones lined with antimicrobial flooring and ozone-treated water baths. Optical sorters remove subpar pieces before packing. The sliced vegetables are packed in modified atmosphere packaging, MAP bags, where oxygen levels are replaced with nitrogen and CO2 to slow spoilage. Bags are labeled with time and date stamps and have a strict shelf life, often just 3-5 days. At the store, staff empty these bags into prep bins, which are rotated based on FIFO, first in, first out protocols. While tomatoes and green peppers may be sliced fresh in store in some regions, most of the work has already been done at the factory. Even cheese is precision manufactured. Subway's sliced American and provolone are pre-cut in industrial dairy plants, where large blocks of cheese are sliced using wire cutters or ultrasonic blades, then interleaved with film to prevent sticking. Shredded cheeses like mozzarella or Monterey cheddar are pre-mixed and coated with anti-caking agents before being shipped in sealed bags. Every item is packed to support Subway's global supply chain. Boxes are coded by product, lot number, and production date. QR codes link to supplier details and quality checks. Temperature sensors are built into pallets to detect cold chain failures. Everything from deli meats to banana peppers is logged, scanned, and traceable. Back in the factories, sanitation is near obsessive. All equipment is cleaned in place daily with caustic foaming agents and food-safe steam. Conveyor belts are removable and made from non-porous plastic polymers. Floors are angled for drainage and cleaned hourly. Workers wear full PPE, including gloves, hairnets, beard guards, and gowns. Entry into production zones requires passing through sanitizing air curtains and foot baths. Factory temperatures are tightly controlled. Cold rooms never rise above 41 degrees Fahrenheit. Warm zones like ovens and proofing tunnels are separated by temperature-locking vestibules to prevent microbial crossover. Air is filtered through HEPA systems to remove particulate matter and pathogens. Every food item undergoes microbiological testing, both at the production site and third-party labs. Products are sampled in real time from the line, plated onto culture media, and incubated to check for E. coli, Listeria, or Salmonella. Batches are not released until testing clears. And then there's distribution. Subway partners with a network of food service distributors who move products from regional hubs to stores every 2-3 days. Trucks are loaded using route-optimized software, and each delivery contains just enough to stock the store without overloading fridge space. Bread dough, meats, cheese, sauces, and produce all arrive together, prepped, chilled, and ready for that made-to-order illusion. In truth, the fresh assembly line at Subway is just the final 5% of a process that begins weeks earlier in factories designed for speed, safety, and consistency. Every slice of meat, every loaf of bread, every spoonful of tuna is measured, packaged, tracked, and delivered to make sure that a sandwich made in Omaha tastes exactly like one made in Orlando or Osaka. So while it may seem like your sandwich is made right in front of you, it's really the result of an entire industrial food system humming quietly in the background, mixing dough, slicing tomatoes, marinating chicken, and portioning cheese by the ton. Subway is a global sandwich brand built not just on customization, but on the relentless predictability of factory precision. And every 6-inch sub starts in a facility engineered to make fresh feel effortless. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than plus 1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada. primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential, not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. The production of Domino's Pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. the yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixes are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conchies are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable Form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs, which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance, particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names. holiday messages, or even national flag motifs. The core of Coca-Cola's production begins at the local bottling facility. These factories are strategically located around the world to minimize transportation time and maximize freshness. While the Coca-Cola Company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger, or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on-site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and checkweighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into six-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remains simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, from syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. To begin understanding how Dr. Pepper is made, we have to step inside one of the massive regional bottling facilities operated by licensed partners. These plants are the heartbeat of the Dr. Pepper supply chain. They don't just bottle soda, they engineer precision, maintain sterility, and manage staggering volumes of ingredients with scientific exactness. Everything begins with water. Although soda is often celebrated for its flavor, more than 85% of the final product is purified water. And not just any water, ultra-clean, neutral, flavorless water that forms the foundation of every bottle. This means municipal or groundwater entering the plant must undergo intensive treatment. The first stage of this treatment process uses coarse filtration to remove large particles and suspended solids. Then, the water is passed through activated carbon beds to eliminate chlorine, chloramines, and any volatile organic compounds that could distort the flavor. From there, the process shifts to more advanced techniques. Reverse osmosis membranes, or ultrafiltration units, strip the water of minerals, microbes, and trace contaminants. Ultraviolet light, or ozonation, finishes the process, sterilizing the water and rendering it free of any taste or odor. The water is now ready, perfectly clean, chemically stable, and ready to receive the flavors that define Dr. Pepper. Parallel to this, syrup preparation takes place in a separate, sanitized mixing room. The base flavoring for Dr. Pepper arrives at the plant in concentrated form, pre-blended by the brand's flavor division under tight secrecy. These concentrates are stored in stainless steel containers and handled with care, with operators measuring and metering the required amounts into large batching tanks. In these tanks, often fitted with high shear mixers, agitation paddles, and precision load cells, the base concentrate is combined with purified water, sweeteners, and acids. Depending on the region, the sweetener may be high fructose corn syrup or cane sugar. The acid, usually phosphoric or citric, helps balance the syrup's pH and sharpness. The mixture is stirred and recirculated until it becomes a uniform, homogeneous syrup with exact Brix values, the measure of dissolved solids in a liquid, often used to calibrate sweetness levels. Before it moves forward, the syrup batch undergoes quality assurance checks. Technicians take samples and run tests in on-site labs, analyzing Brix, pH, color, and aroma. Only after it passes these strict controls is the syrup cleared for the next phase, beverage blending. In a process called proportioning, the syrup is metered and blended with purified water in exact ratios, typically around 1 part syrup to 5 parts water. This mixture becomes the flat, uncarbonated Dr. Pepper base. The proportioning system is controlled by flow meters and programmable logic controllers, ensuring that the mix is stable within a tight tolerance band. Every shift, every batch, whether it's in Texas, Ontario, or the Philippines, must deliver the same flavor profile. With the beverage mixed, it's time to add the fizz. Carbonation is one of the most technically critical steps in soda production. The pre-mixed Dr. Pepper is chilled to just above freezing, typically around 35 degrees, to increase its ability to absorb carbon dioxide. CO2 is stored in large tanks on site and is food grade, filtered, and monitored for purity. The cold liquid is forced through a carbonator where fine CO2 bubbles are injected under high pressure through porous diffusers or sintered steel plates. Proper carbonation is both science and art. If done poorly, the soda may foam excessively during bottling or taste flat when opened. The target for Dr. Pepper is usually around 2.5 to 3.0 volumes of CO2, enough to give it its characteristic zing without overwhelming the complexity of its 23 flavor blend. The carbonated product is now pressurized and ready for immediate bottling to prevent CO2 loss. The bottling line is where everything shifts into high speed. Depending on the plant, the line can handle glass bottles, aluminum cans, or PET plastic bottles. Most modern facilities use stretch blow molding machines to convert PET preforms into full-sized bottles on site. This reduces shipping costs and allows for rapid size changes depending on demand. Each bottle or can first passes through a rinsing or sterilizing system. Bottles may be inverted and blasted with ionized air or washed with ozonated water. Cans are typically rinsed with sterilized water before entering the filler. Now, the carbonated Dr. Pepper is dispensed into containers using a rotary filling machine. This machine features multiple filling heads rotating on a carousel, with each head delivering the precise amount of liquid into each container. The filler operates under pressure to prevent foam and retain carbonation. As soon as the beverage is deposited, the bottle or can is sealed. PET bottles are capped using torque-controlled screw heads, while cans receive crimped-on aluminum lids in a high-speed seamer. Immediately after sealing, the containers pass under printers that apply batch codes, production dates, and expiration information. This coding is essential for traceability. If there's ever a recall or quality issue, the plant can trace every bottle back to the exact minute it was produced, the syrup batch used, and the operator on duty. Then comes packaging. Filled bottles are grouped into packs using shrink film, cardboard sleeves, or trays, depending on the final retail format. These packs are stacked by robotic arms onto pallets in precise configurations optimized for transport. The finished pallets are stretch-wrapped, labeled with shipment data, and moved to the distribution warehouse. But before any pallet is cleared for shipment, the line's quality control team pulls samples from each production run. These are subjected to rigorous testing in the plant's on-site laboratory. Pressure tests confirm carbonation levels. Spectrophotometers check color uniformity. Sensory experts conduct taste evaluations to verify the blend is balanced. Microbial samples are incubated to ensure the product is sterile and safe. Meanwhile, automation software monitors the entire plant. From SCADA systems that track syrup bricks and carbonation pressures to IoT-enabled sensors that measure temperature drift in holding tanks, the entire operation is visible in real time to engineers and technicians. If a motor starts to overheat or a fill level goes out of spec, alerts are triggered immediately. Once quality is assured, the finished product is ready for shipping. Climate-controlled logistics routes transport Dr. Pepper to warehouses, distributors, and retail outlets. Some trucks are refrigerated, especially in hotter regions, to protect the product during transit. Whether it's a vending machine in a high school, a 12-pack in a grocery store, or a fountain soda in a fast food chain, each container of Dr. Pepper must taste exactly the same. And that's only possible because every variable was controlled from start to finish. Beyond the factory, the Dr. Pepper production network also includes specialty manufacturing for fountain syrups, bag-in-box formats for restaurants, and concentrate shipments for international bottlers. These formats go through similar blending, filtration, and quality assurance processes, but are tailored for bulk use with different bricks and carbonation considerations. Every day, this system repeats across dozens of plants, with millions of cans and bottles produced and shipped with extraordinary consistency. Despite being made at different locations by different teams, every unit of Dr. Pepper shares the same flavor fingerprint: sweet, spicy, slightly fruity, with a creamy undertone and a signature bite. It's a beverage born in the 1880s, but produced today using some of the most advanced technologies in food manufacturing. From its mysterious blend of flavors to its perfectly balanced carbonation, Dr. Pepper represents a legacy of innovation, precision, and a dedication to quality that extends from syrup tank to store shelf. Sprite's story begins with water. While most people focus on Sprite's citrus flavor, the truth is, that over 85% of what you're drinking is water. But not just any water. For Sprite to taste exactly the same in Singapore as it does in San Diego, bottling plants must purify their local water supply to a consistently neutral baseline, free from taste, color, odor, and minerals. The incoming municipal or well water is first screened through mechanical filters to remove suspended solids. It then moves through activated carbon filters that strip out chlorine, chloramines, and any volatile organic compounds. This ensures that the water has no off-putting flavors. Then it passes through either reverse osmosis membranes or demineralization columns, which remove dissolved salts and ions. Finally, a UV treatment or ozone injection kills any microorganisms. This ultra-purified water is held in stainless steel tanks, where it is monitored in real time for pH, conductivity, turbidity, and microbial counts. It must meet the exact specifications set by the Coca-Cola company before being allowed into any part of Sprite production. Only once it's passed all quality checkpoints can it be used to create the base for one of the world's most recognizable sodas. Parallel to the water treatment is the preparation of Sprite's proprietary flavor syrup. This part of the process is handled in a syrup blending room, often kept under positive air pressure and high sanitation standards to prevent contamination. The base concentrate used for Sprite, supplied by the Coca-Cola company, is delivered to the plant in sealed, food-safe drums or totes. This concentrate contains the citrus flavoring system, acidulants, and trace aromatic compounds that define Sprite's lemon-lime taste. Inside the blending tanks, equipped with high-torque agitators and recirculation loops, the concentrate is mixed with water and sweeteners to form the final syrup. The sweetener is usually high fructose corn syrup in the United States, though in some countries, cane sugar is used instead. Citric acid and natural flavors help create that sharp, clean taste. The syrup is blended at specific Brix levels, a measure of sugar concentration, and is analyzed for consistency in labs adjacent to the blending floor. Once the Sprite syrup is blended and passes quality checks for color, taste, pH, and sugar content, it is sent to the proportioning system. This is where the final product begins to take shape. Inside stainless steel pipelines, the syrup is carefully metered and mixed with the purified water in precise ratios, generally around 1 part syrup to 5 parts water. This mixture is now the uncarbonated version of Sprite, flat, sweet, and citrusy, but still missing that all-important sparkle. Carbonation is added in the next step. The flat beverage mixture is chilled to near freezing, typically 33 to 36 degrees F, inside jacketed holding tanks. This is essential because cold water absorbs carbon dioxide much more effectively. A carbonator, one of the most critical pieces of equipment in the line, injects high-purity, food-grade CO2 into the chilled mix. The carbonation process is highly controlled. Bubble size, saturation level, and gas purity are all continuously monitored. Sprite generally carries between 2.7 to 3.0 volumes of CO2, giving it that signature effervescence and a sharp bite that enhances the citrus flavor. Once carbonated, the finished Sprite beverage is held under pressure in chilled, oxygen-free holding tanks. It is now ready for bottling, and this is where the production line hits its highest speed. The bottling line is a marvel of automation, capable of processing over 1,000 bottles or cans per minute, all synchronized to fill, cap, label, and inspect each unit with zero tolerance for error. First, the containers must be prepared. If PET bottles are used, they arrive as pre-forms, small, test tube-shaped blanks. These pre-forms are heated and stretch-blown into full-size bottles using high-pressure air inside precision molds. This process allows plants to manufacture bottles on-site, reducing shipping costs and allowing for quick changes in size or shape depending on market needs. The newly formed or delivered containers are then sent through a rinsing or sterilizing station. Bottles may be sprayed with ionized air, steam, or ozonated water to remove dust and kill microbes. Cans are similarly rinsed and then inverted before filling. The carbonated Sprite is then filled into each container using a rotary filling machine. The beverage must be filled under counter pressure to preserve carbonation and prevent foaming. Each filling nozzle is calibrated to deliver an exact volume, down to fractions of a milliliter. As soon as a bottle is filled, it immediately passes to the capping station. Caps and lids are fed in from hoppers and applied with high-speed capping heads that torque each Piet bottle to specification. Aluminum cans are sealed with a crimping mechanism called a seamer, which attaches the lid using multiple rollers in rapid succession. The entire filling and capping sequence is enclosed within a clean, sterile zone to prevent contamination. With the product sealed, it's time for coding and inspection. Each unit is printed with a production code, batch number, and best before date using a high-speed inkjet or laser printer. Advanced camera systems immediately scan the bottles or cans for fill level, cap alignment, label position, and structural defects. Anything that doesn't meet specs is ejected from the line automatically. Now the finished bottles or cans are routed to the packaging area. Depending on the destination, they may be shrink-wrapped in multi-packs, inserted into cardboard carriers, or loaded into trays for larger retail formats. Robotic palletizers pick up these packs and stack them in precise layers, forming stable shipping units. Each pallet is stretch-wrapped, labeled with destination and production information, and scanned into the warehouse inventory system. Before these pallets leave the facility, the Sprite they contain has already been sampled for in-depth quality checks. Laboratory technicians pull random samples throughout each production run and test for bricks, pH, CO2 volumes, and sensory characteristics such as aroma, clarity, and taste consistency. These tests are performed hourly, sometimes more frequently, using calibrated instruments and trained panels. Additional microbiological testing ensures the beverage is free of spoilage organisms. Each batch must pass these hurdles before it is released for distribution. Some plants hold back every 10th or 20th pallet for additional hold and release protocols, where the beverage is stored under controlled conditions and monitored for early spoilage signs before shipment. From here, Sprite enters the logistics phase. Temperature-sensitive loading docks ensure that the product stays cool, especially in hot climates where carbonated beverages can suffer from premature expansion or loss of pressure. Climate-controlled trucks or standard dry vans, depending on the geography, transport the soda to distribution centers, retail warehouses, and vending machine operators. Behind the scenes, the entire operation is driven by powerful software, SCADA systems, programmable logic controllers, and cloud-connected ERP platforms. These monitor tank levels, syrup usage, CO2 flow rates, batch records, and even maintenance needs. Some lines are equipped with predictive analytics, using data to forecast failures before they occur, reducing downtime and ensuring maximum uptime. Every bottle and can of Sprite must conform to the same flavor fingerprint: balanced sweetness, bright citrus notes, clean finish, and a bracing level of fizz. Even with local water, different sweeteners, and various bottling partners worldwide, Coca-Cola's stringent standardization process ensures that no matter where you are, every Sprite you open tastes like it came from the same source. And yet, as science-driven as it is, the drink remains simple in experience. No caffeine, no color, just a bold, clear, citrus-flavored soda that delivers a refreshing hit with every gulp. A product of incredible precision, born in stainless steel tanks, shaped by sensors, robotics, and human craftsmanship, and enjoyed, often without a second thought, by millions. In the end, Sprite may be light and fizzy, but its production is anything but. It's the result of decades of process optimization global logistics, sensory chemistry, and industrial control. And behind that cool green label lies one of the most tightly controlled and fascinating beverage production systems in the world.